We can also have an approximate calculation of the vapor pressure following the phase transition from a liquid to gas using Clausius-Clapeyron equation. So here is the Clausius-Clapeyron equation. dP dt is equal to change in entropy, which is latent heat divided by temperature, and delta V, the change in the volume. So this latent heat is now latent heat of vaporization for the phase transformation from phase 1 to phase 2, where the phase 1 is going to be the liquid. This is latent heat of vaporization per mole. So the first one is the liquid. The second phase is the gas phase, it's the vapor. And V is now the molar volume. So I have, I'm talking about basically 1 mole of a substance that is going through a phase transformation. If you think about how much is the volume change going from liquid to gas phase, V2 minus V1, it's approximately equal to V2 because the vapor vapor volume is typically much greater than the liquid volume, and that's actually something we need to have in order to be able to use ideal gas law, so that we have a low concentration of gas particles. Now, if that is the case, the vapor volume is much greater than the liquid volume, so our container allows this. The vapor can be treated as an ideal gas because it's very dilute. And so we can write PV is equal to nu RT, so pressure P times volume of the vapor is equal to, because volume is molar volume, so it's for 1 mole, it's RT, because nu is 1 here. So we have the change in the volume, delta V, approximately equal to V2, the volume of the molar volume of the gas phase. It's RT divided by P. So if I write Clausius-Clapeyron equation, dP dt, it is latent heat of vaporization per mole divided by temperature multiplied by RT over P. So you can see that I can rearrange this equation. dP over dt is equal to Lp divided by RT square, or I can write this as 1 over P dP dt is equal to L over RT square. Now 1 over P dP dt is actually the derivative of natural logarithm of the pressure with respect to temperature. So we can write the Clausius-Clapeyron equation as del ln P del T is equal to approximately L over RT squared. The approximation comes from the volume, vapor volume, much greater than the liquid volume. So this will give us, if we integrate, natural logarithm of P is from initial temperature to final temperature, L over RT square dt. So standard temperature T0 to T. So this will give us minus L over RT plus a constant. So you can see that the pressure, the vapor pressure, can be written in this form: some constant P0 e to the minus L over RT. So this P0 is a constant, and it came from the choice of our T0. Now, since we typically have the molar latent heat of vaporization or latent heat of vaporization per mole much greater than RT, we see that the pressure is a rapidly decreasing or increasing function of temperature. So as you increase the temperature, the pressure increases rapidly. So that's basically doing this approximation and using the ideal gas law for the vapor. Alternatively, we could use along the phase equilibrium curve the Gibbs free energy per molecule on two sides, the liquid and gas phases, to be the same. We can use this to solve for pressure as a function of temperature from first principles on phases. First principles info on phases. So Clausius-Clapeyron equation is quite useful to get an approximate calculation of the vapor pressure. So previously we talked about solid to liquid melting transition. Now we have vaporization, liquid to gas transition. The Clausius-Clapeyron equation says along the phase equilibrium curve dP dt is L divided by T delta V. And now I'm using this for 1 mole of the substance. So L is latent heat of vaporization per mole. V is the volume occupied by 1 mole, molar volume. The change in the volume going from liquid to vapor phase, I assume, is approximately equal to the volume of the vapor phase. That is to make sure that my vapor is to be treated as an ideal gas. So it's quite low in concentration. So PV2 is equal to nu RT, but nu is 1 mole, so it is RT. So the change in the volume is RT over P, so dP dt is L over T, RT over P. So we can solve for pressure as a function of temperature from this equation to be P0 e to the minus L over RT. So P0 is some constant. So that's the way the vapor pressure behaves. You can see that typically L over R, L is much greater than RT, and P is a rapidly increasing function of temperature. So because it's in the denominator, in the exponential minus factor here, it's in the denominator. So as the temperature increases, the exponential minus alpha factor, the alpha value will decrease. So you will have e to the minus alpha increasing. So it will be an increasing function of temperature. Alternatively, if you don't want to use Clausius-Clapeyron equation, we can go back to the requirement that the Gibbs free energy per molecule on two sides of the phase boundary to be the same to solve for P of T using first principles info on phases as well.